All right, we are now recording. Welcome to physics. I'm going to take roll a slightly different way today. Rather than having you type hello into the chat box, what I want you to do is type in yes or no, depending on the answer to this question. You know how on Friday we set up a big table in front of the school, and everybody was invited to go in and pick up your textbooks. So I'd like to know if you did in fact pick up a textbook. So if you got a textbook, please type yes. If you did not, please type no. All right, so I'm seeing a lot of yeses and a few no's. Okay, so those of you who did not get a textbook, please get one. Now, we're not going to be using it today, and in fact, even on Wednesday, we're not going to be using it on Wednesday. But for sure, starting next week, we will be using the textbooks. So you will absolutely need to have a textbook by next week. So please stop in sometime today. Just go to the office, tell them you need a textbook. They'll take care of you. I hope that everybody has typed into the chat box, because remember, that's the way that I take roll. So if you didn't type either yes or no or some similar thing into the text box just now, you will not get marked present. All righty, let's talk about last night's homework. Before I tell you my impressions of what I saw when I looked at your homework, let me just throw out the question. Do any of you have any questions about the assignment or anything else for that matter? Not hear any questions? Okay, all right. Then let me tell you what I found when I looked at the assignment. Now, I looked at it last night, and I saw that a few of you had not yet submitted it as of last night, but as long as you got it in by 12:44, it'll count on time. But if you got it in at 12:45, it's going to count as late. So Sam is asking, how were you supposed to find the coefficients? Okay, well, we did talk about that in class last time. That's okay, I knew what you meant, don't worry. But let me just go into screen share here. Desmos has a super cool feature. You know how normally you type in something like y equals 2x plus 5, and then Desmos goes and it just automatically graphs that for you? Well, what you can do is you can put in a bunch of table data. So x1, y1, oops, that's supposed to be a y. Sorry, that's supposed to be a y. Okay, and so you put in a bunch of numbers. Okay, and then in Desmos, you create a new expression where you say y1, but instead of saying equal, you put in this mark right there, and then you say m times x1 plus b. And if you do that, Desmos will automatically figure out what your coefficients are. Desmos will find whatever is the m value that fits it the best, whatever is the b value that fits it the best. Okay. Now, this is a good lead into what I want to talk about. Many of you, you thought that a line was the best fit. Okay. But in fact, for this particular data, the data kind of looked like that. So a line, yeah, kind of sort of fit it, but it turns out there's another function that fits it better. And so what you should have put into Desmos is y1 is approximately equal to some letter. I called it a, you can call it whatever you want. If you want to call it m, you can call it that, times the square root of x1 plus b. All right, that is the equation that fits this data the best. Now, when you do that, what Desmos is going to do is it's going to tell you that the a value is going to turn out to be a number that's really close to 2. And don't worry if it's not exactly 2, because it turns out the correct value is not exactly 2. It's really close to 2, but it's not exactly. Okay, so if you got 1.9 something, or if you got 2.1 something, as long as you got something close to 2, I'll call it good. And Desmos is going to tell you that the b value turns out to be a number that's so close to 0 that it might as well be 0. Okay, so when I looked at your homework, I saw that a lot of you tried to fit it to a linear function. And it's not a linear function. So I took off a couple points for that. And I sent you a note saying that if you want to redo this and fit it to a square root function, I'll go back and I'll give you the points that I had to deduct. So I will still do that. And in fact, even though the deadline for this assignment has passed, as long as you turned in something prior to the deadline, I will allow you to go back and revise your thing and fix the little errors that you may have made. And I won't count that as one of your late assignments. And Amy, you can turn it in, and don't worry, I won't count yours as being late because I realize you just joined the class, right? So that's one of the mistakes that I saw, was that you didn't fit it to the square root function. So I see Aurora is asking how many decimal points should you be writing? Actually, next week, we're going to talk about that in tremendous detail. We're going to talk about how many sig figs, how many significant figures are you allowed. And that, if you took Coach Miller's chemistry class last year, then you should already be an expert in sig figs. You should know. But for right now, I'm not going to worry about sig figs this week, but boy, am I ever going to worry about it next week. Okay. All right, a couple other things. Some of you did not label the axes. And I did specifically ask you to label the axes, and I showed you how to do it. So make sure that you do that. So if I docked you a point or two for that, you can go back and correct that if you want. Let's see, what other comments did I have here? Oh, yes. One thing that I did specifically ask you to do, and many of you did not. Okay. So here's your data. So in your x-axis, your independent variable, I asked you to do, a whole bunch of runs all the way from 0.1 up to 1. I asked you to do multiple repeats for each one. So I was expecting your plots were going to look like this. There's going to be 3 data points for that guy, and 3 data points for that guy, and 3 data points for that guy, and so forth and so on. I was expecting to see little groupings of 3. And many of you, in fact, most of you did that. But a lot of you, you just gave me 1 data point here, 1 data point here, 1 data point there. I specifically asked you to do multiple runs. Okay, so again, if I docked you a point there, then you know why. And so please go back and correct that. Okay, Calvin is raising a very good point. Calvin is saying that he did multiple runs, but they were so close together that unless you zoomed in really close on the map, on the chart, they overlapped each other, so it looked like one. Okay, so if I dock you a point for not doing multiple runs, but you actually did do multiple runs, just send me a note through Canvas and let me know, and I'll go back and I'll give you the point that I should have taken off, or that I should not have taken off. Okay. And what else? Oh, okay. Some of you found that if you uploaded a file, it wouldn't let you type into the text box. Okay, because you'll remember that I asked you to upload a file and also to tell me what the equation was. I did ask for both. And by the way, some of you did not do that. Some of you only uploaded the file. And others of you, maybe you gave me the equation, but you forgot to upload the file. So I wanted both of them. Okay, and I took off a lot of points if you only gave me 1. Now, anyway, so some of you noticed that if you uploaded the file, it wouldn't let you type into the text box, but the workaround is that it will let you type into the comments. Okay, so yes, those of you that are writing into the chat box, that is the workaround. You can put the equation into the comments, and that'll get it to me just fine. Okay, good. And I think that's everything that I had to say about last night's homework. Those of you, only a few of you who did not turn in the homework, you can still turn it in. Remember when we talked about this last week, my policy in this class is I do allow 2 late homework assignments per term. I call them late passes. So if you didn't turn in the homework on time, go ahead and turn it in. I will accept it. I will give you full credit even, but it'll use up one of your late passes. Okay. And you've only got 2 late passes for a term. So be careful. You don't want to go using those up, because once your late passes are all used up, I'm not going to give you credit for any more late assignments. All righty. Any questions about that before we move on to today's stuff? Not seeing or hearing anything? Okay. All right, let me go share my screen here. All right, so you should all be seeing my Canvas page now. Let's click on the physics page. And then let's scroll down to the assignments button. And so now my page looks slightly different than yours. So let's go to the flat earth assignment. That is today's assignment. All righty, and if I click on the preview button here, that'll make it so my page will now look a little closer to what your page looks like. Not exactly the same still, but close enough. All right, so who is this handsome young man here who is holding up a Flat Earth Society membership certificate? So what's the deal with that? Oh boy, when I share my screen here, oh dear, it's a monster. Okay, Sam, you are asking for trouble. You are going to get it. Okay, so yeah, that is of course me. And I really am a member of the Flat Earth Society. The name that you see right there, okay, that is my name. I really am a member of the Flat Earth Society. Now, a lot of people say, wait a minute, how can the physics teacher be a member of the Flat Earth Society? Well, the answer is because I really enjoy trolling people. It's a lot of fun. And my fellow members of the Flat Earth Society are the same way. I mean, I don't know anybody in the Flat Earth Society who actually believes that the Earth is flat, but it's a lot of fun to troll people and to challenge their thoughts. And in fact, that is exactly what we are going to do today. All right. So if you were to look on your Canvas page, you will see this assignment, and you'll see that question number 1 starts off with this quote from George Bernard Shaw. So let's see. How about Cindy? Would you be willing to unmute yourself and read this out loud for everybody to hear?
Yeah. We are more gullible and superstitious today than we were in the Middle Ages. An example of modern credulity is the widespread...
Hang on just a sec. So credulity is a word that most high school students, or a lot of high school students, don't know. Credulity is this kind of the same thing as gullibility. So if somebody is really easy to fool, if they're so simple and naive and trusting that they believe anything you tell them, then they're gullible, or we say that's an example of credulity. Okay, so sorry, Cindy, go back and restart with an example of.
Okay. An example of modern credulity is the widespread belief that the Earth is round. The average man can advance not a single reason for thinking that the Earth is round. He merely swallows his theory because there is something about it that appeals to the 20th century mentality. George Bernard Shaw.
Aha. All right, so question number 1 on your homework assignment for today is, let's see if George Bernard Shaw was right. So what I want you guys to do in the text box on question number 1 here is I want you to list as many reasons as you can. Now, actually, I should have reworded that. Just one was good enough. If you can give me one reason for why you should believe that the Earth is round rather than flat, that's what I want on here. Now, notice I'm giving you some important constraints here. I am not going to allow you to rely on observations or measurements that are made by other people. Especially, I'm not going to allow you to include photographs that were taken by NASA astronauts, because I'm sure you guys know NASA is part of Obama's deep state conspiracy, right? So we can't trust NASA. Heaven forbid we do that, okay? So you lost a few brain cells, huh? Well, wait till the day is over. You're going to lose some more, but hopefully you'll gain even more than you lose. Okay, so I am not going to allow you to give any evidence that's obtained by people other than you. Okay, only include observations or measurements that you yourself could personally do. And I'm going to put another caveat on here. I'm going to say you're not allowed to leave the state of Utah. And I have to do this because if I allowed you to get on an airplane and fly around a whole bunch of places, then it turns out it would actually be pretty easy to prove that the earth is not flat. And so I don't want it to be too easy. I got to make it challenging. So your job here is prove that you can prove to me that me and my friends at the Flat Earth Society are wrong. Okay, but you can only use observations that you yourself could do without leaving the state of Utah. Okay. Now, I'll pause for just a minute. Does anybody have any idea of how you might do that? Okay. All right. So Sam is thinking she can maybe do something with the rotation of the Earth. Connor is thinking maybe there's something about the sunset, sunrise you could do. Taituan typed an upper caret in there. Okay. Oh, Will is suggesting we look at a lake. Can you elaborate on that, Will? Can you unmute yourself? Just push.
Yeah, I was getting there.
Okay. Very good.
Well, so basically, if there is no curvature on the planet, if we were to look at something really flat, and in this case, like a really big lake, so the Salt Lake, for example, if the world is completely flat, you could hypothetically see much, much further instead of, just seeing how the lake just continues to be flat. You could probably see, I don't know, mountains on the other side or something.
Okay, I like where you're going with that. There are a few things that me and my friends of the Flat Earth Society could bring up to argue against that. In fact, that's why it's so much fun being a member of the Flat Earth Society. I recommend that you guys go on their website, and they have a whole section there where people submit arguments to them that people think proves that the Earth isn't flat. And then me and my friends of the Flat Earth Society, we come back with good counter arguments. And it's a lot of fun. So yes, Sam, I'm definitely trying to brainwash you here. So it's actually a lot of fun being a member of the Flat Earth Society, but remember, all I'm doing is trolling you here. Okay, so what we're going to do for today is we're going to talk about a couple of techniques that people think might possibly prove that the Flat Earth Society members are wrong. And then we're going to talk about one method that even me and my friends of the Flat Earth Society can't argue against. It's such a good argument. Okay, so let's go on to question number 2 in tonight's homework assignment. And by the way, what you guys are going to find is that I am going to basically give you the answers here to tonight's homework. So don't get in the habit, don't think that I'm going to do this all the time. The reason I'm doing it today is just because I'm such an incredibly nice guy, and I want you to start off the year easily. Up at the top of the page here is something that's really important. The purpose of what we're going to do today is not really to troll people about flat Earth, is to show you how it's possible to prove that the Earth is not flat using a technique that we're going to be using all year long. What we're going to do is we're going to create what's called a mathematical model for the flat Earth hypothesis. And we're also going to do one for the round Earth hypothesis. So we're going to have 2 mathematical models, and you're going to find out in just a few minutes what I mean when I talk about a mathematical model. So if you don't know what that phrase means right now, wait a few minutes and you'll find out. But basically, we're going to create a mathematical model, and then we're going to compare the actual data and see which model fits the data the best. All right. So in question number 1, hopefully you guys are going to come up with some creative ways to prove to me that the Earth is not flat. It turns out there are a whole lot of ways you can do it. but we're going to focus on just one of the arguments today. And the argument that we're going to focus on is something that sailors have known for centuries, and other explorers have also known it for centuries. The angle of the North Star in the sky, it gets lower and lower and lower the further away you go from the North Pole. So imagine this. Imagine that you're standing at the North Pole. So the North Star is going to be directly above your head. Okay. So what you're going to do is you're going to take one arm and you're going to point one arm at the horizon. Okay. You're going to take your other arm, you're going to point your other arm at Polaris. Now, if you're at the North Pole, it's going to be directly above your head. So the angle in between here is going to be 90 degrees because Polaris is directly above your head. All right. Now, as we go further south, what we're going to see is that Polaris gets lower and lower and lower in the sky. So if we point one arm at the horizon and the other arm at Polaris, the angle is no longer 90 degrees. The further south we go, the smaller that angle gets. And if you look at this picture here, right, it should be pretty clear why that's the case. Now, a lot of people think, well, this proves that the Earth is flat, this proves the Earth is not flat. Sorry about that. Because you can see the picture here. The picture explains what's going on. As you get further and further south, the angle gets smaller, right? And now, actually, let me go back to the previous page here. There's one thing about my drawing here that you need to understand, okay? Remember how I said that Polaris is above the North Pole, but my drawing here shows that it's not, okay? According to my drawing, okay, Polaris is over here, but you're saying, wait a minute, Mr. Hendricks, I thought you said that the Polaris was above the North Pole. Well, the thing is that Polaris, which is another name for the North Pole, in case I forgot to tell you, Polaris is actually 400 light years away. That is so incredibly far that it's way, way, way up there. It's so far, there's no way I could possibly show this on the page, all right? So if a person standing at the North Pole points their arm at Polaris, okay, their arm is going to look like this. And if a person standing anywhere else on the Earth points their arm at Polaris, those two fat lines that I just drew there are going to be so close to being parallel that there's no way that here on Earth you'd be able to tell they aren't parallel. Now, in reality, Polaris is not infinitely far away. So, I mean, if Polaris was actually up here, then the person down here, when they point their arm at Polaris, they're going to point it like that. And the person on the North Pole is like that. So those two lines are not actually going to be perfectly parallel. But if Polaris is 400 light years away, which it is, then those two lines are going to be so close to parallel that you would never be able to tell they weren't parallel. All right. All right. Now, a lot of people think that this is a great way to prove that the Earth is not flat. So if you look on the Flat Earth Society website, you'll see that this is one of the arguments that people say. They say, ha ha, because we know that the further south people go, the lower Polaris becomes in the sky, and therefore that proves the Earth is not flat, right? If you look at this drawing right here, you can see, so here is a person at the North Pole. So obviously for them, Polaris is directly overhead. Now here is a person who's a little bit south of the North Pole. And remember, if Polaris is 400 light years away, so it's as good as being infinitely far away, okay? No matter where you are on the Earth, Polaris should always be at an angle of 90 degrees if the Earth is flat, okay? So you can see how a lot of people, they say, ha ha, I've just proven to you that you're wrong, the Earth is not flat. Do you guys agree that this is pretty good evidence that the Earth is not flat? Well, it turns out, me and my friends at the Flat Earth Society, we don't give up easily. And so when people tell us that they think that that argument proves the Earth is not flat, we have a comeback for that. And our comeback is this. We claim that whoever it was that told you that the Polaris is 400 light years away, they're lying to you, okay? Polaris is actually not 400 light years away. Polaris is actually just a few thousand miles above the Earth's surface, okay? Now, so what this means is that if anybody wants to believe that the Earth is flat, they also have to believe that Polaris is not infinitely far away. Okay, so if you accept my argument that Polaris is really not infinitely far away, then all of a sudden it makes sense that the further south you go, the smaller the angle becomes, right? So, oops, let me, didn't mean to do that. Let me turn on annotation. Okay, all right, so if you're at the North Pole, then yes, I agree, Polaris is going to be at an angle of 90 degrees. If you go further south of the North Pole, then yeah, okay, I agree that the angle is going to get smaller. And the further south you go, the smaller the angle gets. So if you think that the fact that the further away from the North Pole you get, the smaller that angle becomes, if you think that fact proves that the Earth is not flat, then I say, then what I say to you is neener, neener, neener. I don't accept your argument. Okay. All right, so you're gonna have to come up with a better argument. Well, let's do that. Let's come up with a different argument, whether it's better or not, we'll see. Okay, and by the way, everything that I'm talking about right here, I'm basically giving you the answers to the homework assignment. So if you are taking notes about what I'm saying, all you have to do is just put it into your own words and type it in the text box here, and I'm giving you the answers. But remember, don't get used to that because I'm not going to do that going on here. Okay, so the round earthers, the people that I call globe heads, right? The globe heads say, well, okay, here's another argument for why the Earth can't be flat, okay? The further south you go, the smaller the angle becomes. What happens when you get to the equator, right? You see that? When you get to the equator, if you point one arm at the horizon and you point the other arm at the North Star, well, they're both equal to each other. So when you're at the equator, the North Star is sitting on the horizon. And then here's the good part. When you get down below the equator, so here's the horizon right there, the North Star is below the horizon. You can't see the North Star anymore, it's blocked, okay? And in fact, this is what happens. This is an indisputable fact. Okay. So me and my friends of the Flat Earth Society, we cannot argue with the fact that when you get down in the Southern Hemisphere, the North Star disappears. Okay, you cannot see the North Star from the Southern Hemisphere. We cannot argue with that observation. In fact, you know, many of you guys know that I'm really into sailing. I spend my summers out on the ocean sailing, and I even took 1 year off and just sailed all over everywhere. So I can verify from my own personal experience that it's true that when you sail across the equator and you get down the Southern Hemisphere, you can't see the North Star anymore. So people who think that the Earth is round, you know, the globe heads, okay, they think, ha ha, I've just proven that the Earth is not flat. Well, as I said before, me and my friends in the Flat Earth Society, we don't give up very easily. We have a counter argument for that. Here is a picture that explains how our counter argument works. Now, this thing that you see right here doesn't have to be a cloud. It could just be haze, which is basically, you know, water vapor. Okay. So even if there are no clouds in the sky, there's still water vapor, there's still haze in the sky. And so when you're at the North Pole and you're looking at the Polaris, you're looking through a very thin layer of haze, and so you can see the North Star really well. You get further south, you're still not looking through that much haze. When you get down near the equator, or especially if you get down past the equator, you're looking that light has to travel through a big, long layer of haze. And so because of that, that's the reason why you can't see it anymore. At least that's what me and my friends at the Flat Earth Society argue. Okay. So you can see that we are tenacious. We want you to really think through a good, solid proof. If you want to prove us wrong, you've got to have a better proof than the ones that we just talked about. Okay. Now, for question number 1 in the homework assignment, I'm hoping that you will come up with a good, solid proof, one that me and my friends at the Flat Earth Society are unable to argue against. But just in case you can't, I'm going to help you out. All right. Let's move on to question number 7 in tonight's homework. Okay. I'm going to give you a strategy for proving one way or the other whether or not the Earth is flat. And this is a strategy that me and my friends at Flat Earth Society are not going to be able to shoot down. What we're going to do is we're going to create a hypothesis. So actually, we're going to have 2 hypotheses. We're going to have one for the flat Earth and one for the round Earth. So we're going to say, okay, let's temporarily at least, let's assume that the Earth actually is flat. All right. And then we're going to think of an experiment, and we're going to say, when we conduct this experiment, if the Earth is flat, then the data should look like this. Whereas if the Earth is round, then the data should look slightly differently, maybe dramatically differently. And then we're going to compare that with actual data, and we're going to see, does the data fit the round Earth hypothesis better, or does it fit the flat Earth hypothesis better? Okay. So here's the experiment that we're going to do. Okay. We're going to imagine that, so we're going to imagine that we start at the North Pole, just like we talked about before. Okay, so we start at the North Pole. We got one arm pointed at the horizon, the other arm pointed at Polaris. We measure the angle. We go further south and we repeat the experiment. Now, rather than using our arms, I would recommend that we use a tool like this. This is a protractor, like this ones that you've used in your math classes, except I've got a straw taped to the top, and I've got some sort of a weight hanging on a string down here. All right, so if I look at the horizon, this thing's going to hang straight down. If I'm looking at something that's a little bit higher, you can see it hangs down here. So all I have to do is see how many degrees is it from here to here. I can just count the number of degrees, and that'll tell me that what Polaris's angle is. Now I'm going to call that the altitude, that the angle that I measure here, the angle between the horizon and where Polaris is, that angle, I'm going to call that the altitude. And so we're going to conduct an experiment here where the independent variable in our experiment is going to be how far south we are from the North Pole. So let me highlight that right there. Because so the independent variable is our distance from the North Pole. The dependent variable is going to be the angle of Polaris above the horizon. All right. And so then the way we're going to determine whether or not the Earth is flat is we're going to come up with a mathematical model, an equation that tells us how those 2 variables would have to be related if the Earth is flat. And then we're going to do it again. We're going to say, what do these equations have to look like if the Earth is round? And then we're going to compare that with the data. Now, there's a special terminology that I want you guys to get used to using. Okay, and so this is the way that I'm going to say it. I'm going to say that we're going to create a mathematical model for each of our hypotheses. So get used to this terminology, because as the year goes on, we're going to be using this terminology a lot. That's the reason I'm doing this experiment, is to show you this is how physicists do physics. We come up with a hypothesis. We think of some experiment that we can do. And then we say, okay, if our hypothesis is true, then the data needs to follow this equation. And then we look to see, does the data follow the equation? right? Hopefully that's pretty straightforward. So get used to it, guys. This is what we're going to be doing for the rest of this year with other types of data. All right, so let's start with the round Earth hypothesis. My internet is loading really slowly. There it goes. Okay, so I'm going to start with the hypothesis that most of you claim to believe, the round Earth hypothesis. So I'm going to take a poll here in just a minute. So our independent variable is going to be the distance from the North Pole to where we are. Okay, that's our independent variable. Let's call that x. So that's the distance. Now our dependent variable is going to be the angle of Polaris. Okay, so this angle that you see right here, that's it. All right, so you know what our independent variable is, you know what our dependent variable is. All right, let's take a poll here. I'm going to ask you the same questions that I asked you on the first day of, or in the first week of school. So do you think the relationship between these two variables would be a direct relationship or an inverse relationship? And at the same time, I also want you to ask, do you think that the relationship between these two variables will be linear or nonlinear, assuming that the Earth is round? Remember, this is important. We are assuming, for the sake of argument, that the Earth is round. So will they be direct or inverse? Will they be linear or nonlinear? Everybody has to answer. All right, so far 10 of you have answered. Keep going. We're not going to move on until everybody has answered. Okay, you still need one more. Oh, there we go. Okay, good. Everybody has answered. All right, let's see what you said. Okay. 4 of you said that it would be a direct relationship. 13 of you said that it would be an inverse relationship. So this is one that I would hope would be pretty straightforward. So if we graph these two, so here's our x, here's our y. If we start off at the equator, so the distance equals 0, the angle equals 90 degrees, so 0, 90, that's where we start off. Okay, as we move away from the North Pole, the angle gets smaller, not bigger. So the 4 of you who said this is a direct relationship, you need to go back and rethink this. Okay, this is not a direct relationship. This is an inverse relationship. Okay. Oh, I see. Okay, so people are saying that you misclicked. Okay, that's understandable. Okay. Now, so the direct versus inverse, I would hope that you guys agree this one's obvious. Now, the linear versus nonlinear, okay, maybe not quite so obvious. 7 of you said it would be linear. 11 of you said it's not, would be nonlinear. Yeah, this one is one that I'll agree you need to think about a little bit. But if you do think about it a little bit, it should become pretty clear. So down here, this angle right here, let me clear that again. Let me try that. Okay. This angle here, this is your latitude. You guys remember when you took Mrs. Tilden's geography class, you learned about latitude and longitude? So latitude is the angle for how far you are above the equator. This angle here is Polaris's altitude. And it shouldn't be that, in fact, it's not that hard to prove. These two angles have to be exactly the same. Now, I don't want to take the time to prove that in this class, but it's not difficult using the techniques that your math teacher should have taught you. Remember about vertical angles and alternate interior angles and all that good stuff you learned in your math class. If you use those techniques, it's not hard to prove that these two angles have to be exactly the same. Right? So if you go down 1 degree in latitude, then Polaris's altitude is going to go 1 degree. And it doesn't matter whether you're up here in Alaska or whether you're down here in Panama or anywhere in between. 1 degree change in latitude equals 1 degree change in Polaris's altitude. So with that, hopefully you can see that it must be a linear relationship. So if I were to graph these, whoops, let me get rid of this. All right. So if when you take the quiz here for real life, in the homework assignment, you need to retake the quiz that we just took, and I'm hoping that you'll get them right this time. When you get up into question number 9 of the homework, you'll see that it's asking you to make a sketch of what it should look like. Well, we just got through saying that it is a linear relationship. So if we start off here at the point 0, 90, and it goes, and we know it's a linear relationship. So if it starts off down, it has to continue going down. So that means it must reach 0 at some point. Okay. And in fact, you can see it even goes negative here, which, yeah, makes sense. When you get down in the southern hemisphere, yeah, the Polaris is definitely going to be below the horizon. So it makes sense that it would be negative, right? So this is what the sketch should look like. Now, notice I have told you here how far it is from the North Pole to the equator. So if you start at the North Pole and you keep on walking and you keep on going until you get to the equator, you will have walked 6,215 miles. This means that we know what the coordinates of this point are. So this coordinate, the coordinate of this point right here is 6,215-0. All right, everybody agree? Now, here is a neat part, okay? On question number 9, all I asked you to do was to sketch the graph. But in question number 10, I want you to come up with the equation. Now here, this is one part that I am not going to do for you. You should know how to find the equation of a line. If you know the coordinates of 2 of the points on the line, you should be able to find the equation that fits that line. Right? So I'm trusting that you guys can do that. So let's just go ahead and move on to the next question. So I'm not going to help you with this one. This is one that you should be able to do by yourselves. Now let's do it again, except this time we're going to do it for the flat Earth hypothesis, right? So we are going to assume, at least for the sake of argument, we're going to assume for a few minutes that the Earth actually is flat, okay? So I'm going to ask you the same question that I asked you before. In fact, I'm going to relaunch the poll here. Okay. Now remember that this time when you answer the questions, we are assuming that the Earth is flat. Let's see if that changes your answer to the questions. So if the Earth is flat, do you think that it'll be a direct relationship or an inverse relationship? Do you think it'll be linear or nonlinear? Everybody needs to answer. All right, about half of you have responded. The rest of you, you still need to do it. Come on. Okay, good. The answers are coming in. All right, I need 3 more people to respond. The reason I'm laughing is because of Sam is typing in funny things into the chat box here. Yeah, let's find out if we're flatheads or if we're globe heads. Let's find out. All right, I need 1 more person to respond. Come on, who's the holdout here? Well, I'll tell you what, okay, rather than waiting, I'll go ahead and I'll end the poll and let's share the results. Okay, this is really, really, really interesting to me, actually in a sad way. Half of you said that you think it's going to be a direct relationship. Okay, what this tells me is that you guys are still not really understanding what it means to be a direct relationship. Okay, if I draw a graph here, if it's a direct relationship, it should increase. Remember, our independent variable here is the distance from the North Pole to where we are. Our dependent variable here is the angle. You can see it starts out big. As this distance increases, the angle gets smaller. As you get even more, it gets smaller. So that it does not look like this, okay? It looks like this. It starts off here and it goes down, right? So half of you, let me wag my finger at you here. Half of you still not really solid on what it means to be a direct relationship or an inverse relationship, even after everything that we did last week. So we've got to up our game here, guys. You should have been able to get this one right. Now the linear versus nonlinear part, that's a little bit trickier, but not much. More than half of you said that you thought it would be a linear relationship. So 11 of you said that you thought it would be linear, right? Again, this is one that I think you should have gotten right. Look what happens as the distance gets bigger and bigger and bigger. Okay, so as we go further away from here, the angle gets smaller and smaller and smaller. We could go all the way out to infinity. Is that angle ever going to get to zero? The answer to my question is no. The answer, that angle will never ever get to zero. So if I were to graph this, okay, here's my independent variable is the distance. My dependent variable is the angle of Polaris. We start off at the point 0, 90. We start heading downward, but here's the important thing. If it was a linear relationship, if it starts off downward, it has to continue going downward. Does that make sense? If our plot starts off heading downward, if it's a linear relationship, it has to keep on going downward. At some point, it will reach zero, and in fact, it will go negative. But as you can see from over here, even if you go all the way out to infinity, it never, never, never reaches zero. So if we plot the relationship here, distance here and angle there, it starts off, but then it levels out. It approaches zero asymptotically, but it never reaches zero, right? So even before we do this experiment, we know that it can never possibly reach zero. Therefore, it cannot be a linear relationship, right? So this is one that I would hope that you guys would have gotten right. But in the homework tonight, you can ask it again, and hopefully you'll get it right in the homework tonight. All right, so let's move on. So question, oh, come on, why is my internet so slow? All right, so question 11 was the direct or inverse. Question 12 is the linear nonlinear. And so we have now gone over the answers. So if you don't get these right on the homework tonight, you got no excuse whatsoever. And we've already done question number 13 for you as well. We've sketched the graph, all right? So I'm doing your homework for you tonight. Don't get used to this. I'm not going to keep on doing it, but I will for tonight. All right, let's move on to question number 14 now. This is the fun part. This is the real challenge in tonight's homework. What we need to do here is we need to find the equation of this graph. So let me turn this back on here. So we're all agreed that if we graph the distance and the angle, we start off at 0, 90. We start off heading downward, but then it approaches zero asymptotically. Do you think we have enough information to where we could figure out what this equation is? Well, I'm going to answer that question for you. The answer to that question is no, we don't have enough information. We need to get some other point here. We need to find out at least one other point. What are the coordinates? What are the x, y coordinates of some other point? Now, when we did this for the round earth theory, we knew that once we get to the equator, we knew that the angle went to zero, but that's not the case here. So we need to find some other point. How can we do this? Well, let me tell you. Okay. What we need to do is we're going to use this tool. So here you see we've got the protractor, just like I talked about before. And what we're going to do is we're going to assume that we go outside tonight and we measure the altitude of Polaris from here in Salt Lake City. And then that will give us the other point that we need. Okay. All right. Now I'm not going to make you guys do it. I'm going to tell you what I got when I did it. All right. When I did this the other day, I went outside, I measured the angle of Polaris, and I got the number of 40.75 degrees. Now, some of you, hopefully, are going to say, you're going to say, wait a minute, Mr. Hendricks, I don't believe you. Because if I'm going to use this tool right here to measure the angle of Polaris, if I report my results as being 40.75, that means that I am confident that it's more than 40.74 and is less than 40.76. So I'm claiming that I know what the angle is to 1/100th of a degree using a tool like this. No way. No way you can get that kind of accuracy using a tool like this. So you guys are probably say, well, Mr. Hendricks, I don't believe you. Well, I didn't use this tool when I measured it. I used this tool. Right? Remember I told you that I'm really into sailing? I spend all my summer sailing. Yeah, this is a sextant. And I'm not going to take the time to explain to you how a sextant works. But basically, I can look at Polaris through here and I can bring it down and I can read it. And with the sextant, I really can get an accuracy of 1/100th of a degree. It is possible to do that. And by the way, next week, we're going to talk a lot more about precision and accuracy and significant figures. So Aurora is saying that the Flat Earth Society is really scientific. Yes, actually we are. We are very, very scientific. That's why nobody in the Flat Earth Society actually believes that the Earth is flat. Okay, but don't tell anybody I said that. All right. So let's go back to here. All right, so we're going to suppose that we measure the altitude of Polaris from Salt Lake City and we get 40.75. Okay, well, we now have enough information to where we can now figure out the equation. But it's a little bit tricky. We're going to have to do this in 2 steps. So the first step we're going to have to do is we're going to have to find out how high Polaris would have to be above the equation, above the ground, in order for the Flat Earth Society to have any hope of being right. All right, let's take a minute and let's see how good you guys are at trigonometry. Remember trig? Remember sines, cosines, and all that bunch of stuff? In fact, tell you what, I want to take another poll. This time I'm going to do it via the chat box. All right, I want everybody to type into the chat box either yes or no. And the question that I want you to answer is, have you learned in your math class about sines, cosines, and tangents? All right, which is also called trigonometry. So if you have learned about sines, cosines, tangents, type yes. If you have no idea what a sine, cosine, or tangent are, you've never talked about it in your math class, I want you to type the word no. Right? So I see most people are typing in yes. A lot of people haven't typed in yet. Come on, I need everybody to type in here. All right. Okay, looks like the overwhelming majority of you have. Okay, those of you that typed no into the chat box, I want you to hang around at the end of class today. When I let everybody else leave the meeting, I'd like you to stick around. We need to talk one-on-one. Yeah, SOHCAHTOA. Yep, that's it. That's exactly what we're going to do. All right, so those of you who don't know about sines, cosines, tangents, what we're about to do is going to be a little bit of a mystery to you, but the rest of you should be good. Now, it will be a review. I see a lot of you, when you typed in your answer, you said that you learned about it, but it was a long time ago and you're not confident in it. Don't worry, you'll get it. All right, so let's think of this as a math class, because physics really is just applied math. We've got a triangle here. It's a right triangle. This is 90 degrees. This angle here is 40.75, This side of the triangle here is 34.01. And I want to know what is H. So think for a minute here. Is this going to be one that we need to use the sine for? Or is this going to be cosine? Or is this going to be tangent? Which one of our three friends is going to help us out here? All right, I'm seeing a lot of people are saying cosine, or at least some people are saying cosine, but saying it with a question mark. Okay, other people are saying, I've forgotten how to do that. Okay, all right, let's do a quick review of mathematics. All right, so if this, let me turn on my annotation here. If this is the angle that we know, okay, this side right here is the hypotenuse. Okay, this side right here is the opposite side. This side right here is the adjacent side. All right, now we know what the adjacent side is. We want to know what the opposite side is. So I'm thinking cosine isn't going to work because cosine is the adjacent divided by the hypotenuse. Okay, all right, we don't know what the hypotenuse is. And what we want is the opposite side. So cosine's not going to help us because it doesn't even have opposite in there at all. All right, that's no good. All right, so it's not the cosine that's going to help us. What we need is another one. So I see that, okay, it looks like you guys have all agreed now tangent is what we want. So I agree. So the tangent of theta is defined as the opposite divided by the adjacent. And yes, that is in fact the one that's going to help us out here. Okay, so let me clear all this out here. All right, so the tangent of the angle, which in this case is 40.75, is equal to the opposite side, which we don't know, so we're going to call that H, divided by the adjacent side, which we do know. So that's 3,401. All right, now it's just algebra. The trig's all done. Trigonometry, we're over with that. Now it's algebra. We want to solve for H, okay? So what do? Well, let's just multiply each side by 3,401. And, okay, all right, so that cancels that. Whatever we do the left side, we have to do the same, or whatever we do the right side, we have to do the same thing the left side. And so here's our answer. So H then equals 3,401 times the tangent of 40.75. Has anybody punched that out in your calculators yet? Somebody please punch it out and tell me what number you get. All right, Cindy is saying she gets 2,930. Anybody second that motion? Okay, looks like Calvin seconds it. All right, any opposed? Nobody opposed. All right, now we know what H is. H is 2,930. All right, so what this means is, in order for me and my friends of Flat Earth Society to have any hope of the Earth actually being flat, Polaris cannot be 400 light years away. Polaris has to be 2,930 miles away. Okay, well, that's fine. We can go with that. All right, we're going to assume that. And, okay, so I've just worked, or we have together now worked out the equation or at least step one, the answer for question number 14. I hope you guys are taking good notes, because all you have to do tonight is basically just type that into Canvas for tonight's homework here. All right. Calvin is saying it's closer to the North Pole than Salt Lake is. I have no idea what you mean by that, Calvin. What is this it that you're talking about? I don't know. All right, let's move on. Oh, Polaris. Oh, okay, gotcha. Yes, Calvin is absolutely right. Polaris is closer to the North Pole than Salt Lake is if Me and my friends of the Flat Earth Society are right. Okay, now that we know that, now we're ready to go to step 2. So step 2 is to find the equation for our function here. So remember, we have decided that if the Earth is flat and we graph the distance as our independent variable and theta as our independent variable, we know we're going to start at the point 0, 90. We know we're going to go down, and we know it's going to go asymptotic like that. And now we know that other point that we didn't know before. We know that when we're in Salt Lake City, when the distance equals 6,000, I forgot already, 6,000 what? Somebody help me out. 6,000 and whatever it was. I don't want to quote the wrong number here. But anyway, we know the coordinates of this point here. So I should have written this number down. Somebody help me out. Did anybody write down what the distance was for? Oh, it was 3,401 was what it was. Okay, sorry about that. Let's try that again. Okay, so if we're in Salt Lake City, which is 3,401 miles away from the North Pole, then we know the angle is going to be 40.75. Okay, so we have the coordinates of that point, we have the coordinates of that point. We are good now. We can now figure out what the equation of this curve is. Anybody know how you could do that? So h now is a known number. Let me clear out all the drawings here. H is a known number now. H we know is 2,930. So the distance here is not going to be 3,401 anymore. This distance here is going to be whatever we want it to be. All right, so how can we figure out what is theta as a function of distance if we know that Polaris is 2,930 miles above the Earth? How could we do that? All right, not seeing any suggestions. All right, let's open up a whiteboard here. Remember the definition of tangent? Tangent of theta equals opposite over adjacent. Okay, well, we want to keep that generic, so we're going to keep theta like that. That's theta. It's a terrible theta. But what we do now know is we know what the opposite side is. We know that the opposite side is 2,930. The adjacent side, that's the thing that, oops, I didn't want that to be an H, sorry. Right. The adjacent side, that is going to be just any old generic D. All right, and also while I'm at it, that was a terrible, terrible theta. Let's clean up that theta there. All right. Okay, thank you. All right, much better now. Okay, so we want to solve this equation for theta. How do we get rid of that tangent? Do we divide both sides by tangent? Is that how we do it? Ah, okay, so Will is suggesting that if we divide by tangent, that's not going to work because it's not tangent times theta, it's tangent of theta. So what we're going to have to do in order to get rid of this guy is we're going to have to take the inverse tangent, okay, and whatever we do to the left side, we have to do the same thing to the right side. Okay, so when we take the inverse, whoops, where'd it go? Did it? Oh my goodness, it all just went away. Oh, okay, all right, here we go. Okay, so when we take the inverse tangent, that canceled the tangent, leaves us with just theta. And so then on the right side, we're going to have the inverse tangent of 2930 divided by D. Bingo, there we go. Okay, this is the equation we're looking for. So if we were to graph d on the independent variable, theta on the dependent variable. We're going to get a graph that looks like this. And what you see here is the equation of that curve. You guys see how it works? So now all we have to do in order to see if whether the Earth is flat or not is we have to take this mathematical model that we just created, compare that with actual measured data, which is something that you could do yourself. Now, if you did it yourself, you'd probably have to use one of these tools, because I doubt if any of you have a sextant, right? But, you know, you could do this, and you could do this without leaving the state of Utah. You could go up to Logan, and you could measure it in Logan, and measure it again in Provo, measure it again in Salt Lake, and measure it again in St. George, and go all the way down, and compare that data with your mathematical model, and then see which mathematical model fits the data the best. Does the flat Earth model fit it the best, or does the round Earth model fit it the best? Right? Okay, let me skip on to here. All right. Well, we are going to stop here today. We're not actually going to do the comparison today because I knew ahead of time there wasn't going to be enough time to do everything today. All right. So all you have to do today is basically just regurgitate what we just did. There's only one thing that I haven't done for you, and that's find the equation of the round Earth model. Okay, that's something that I believe you guys should be able to do without help. The flat Earth model, that one was a little trickier. I realized that if I asked you guys to do that one, probably most of you would not have been able to do it on your own, at least not at this point in the year. Now, later on in the year, I am trusting that you guys will be able to do stuff like that. But right now, yeah, I understand you just got off summer vacation, so fine, I helped you out with that. But you have to do the round Earth model. And other than that, if you just take everything that we talked about and just type it into Canvas, you will be done with tonight's assignment. And next time we meet, what we'll do is we'll compare it with the actual data and we'll see what fits it the best. All right, are there any questions about what we just did? Not hearing anything, not seeing anything. Okay, then what I want you guys to do, remember I take roll at the beginning of class and I also take roll at the end of class. Therefore, before you guys leave the meeting, okay, so we do have a question. So Adam's saying that you might want to watch this again. Yes, so we are recording this and I do recommend that you put on, so it takes a couple hours to process the recording. So it won't be up on the video or it won't be up on Canvas until later this evening, but sometime this evening, I will have a recording of this class up on Canvas. So definitely watch it again and hopefully it'll make more sense the second time around. And also before you guys log off, a couple things. Number one, those of you who said that you never learned about sines, cosines, and tangents, I want you to stick around after everybody else logs off so that we can talk privately. And I'll even turn off the recording so that you don't need to worry about being embarrassed. And then the other thing is those of you who are ready to leave the meeting, remember, I want you to say bye in the chat box before you go. So as soon as you say bye, you can go ahead and log off, except for those of you that don't know about sines and cosines, you got to stick around. I'm going to turn off the recording right now so that we can talk without you guys being embarrassed.